Hi, I'm Juliette, and this is my lab report for Lab 5 about energy. And so, in this lab, I'm examining the motion of a system using the fundamentals from the energy principle. For my video, a ball is being thrown in the air in an arc motion. My system is the ball, and we are dealing with gravitational and drag interactions. I will use Tracker to extract and analyze the position data of the ball in my video. And then, like other labs, I will then use GlowScript to create a model replicating the motion by using the energy principle. I will obtain the data and later determine how much energy is exerted on the ball when it is thrown. I will compare my models as well as use Newton's second law to analyze and observe the position's updated position and velocity over a given time interval. The purpose of calculating how much energy it takes to throw the ball is that we can later calculate how many throws it takes to burn your daily amount of active calories. In this lab, I use the work and energy principle, which states that the total energy of a system will stay constant unless there is an outside force that does work on the system. I then used gravity to predict the motion, knowing that the attraction between our object with a mass and the Earth is negative mg. The equations I used in my code that are associated with energy were that kinetic energy equals 1/2 mv squared and potential energy due to gravity equals mgh. I then used Newton's second law and the momentum principle to update the position and velocity of my object. The purpose of my lab was to find out how many times he throws it takes to burn off your daily amount of active calories, and so we can convert the energy of our object to calories by using the conversion factor of 1 calorie and calculating the total energy of the object in joules. I used Tracker to analyze the exact motion of my object along the y-axis. My initial position was 0.133 in the x direction and 2.905 times 10 to the negative second in the y direction. My initial velocity, which I found by doing the total change in position over the total change in time, was 1.56 in the x and 2.14 in the y. The mass of my ball was 0.282 kilograms. The gravitational constant is 9.8 meters per second squared, and there are 4.184 calories per joule. So the first thing I did in my code was program the visuals. So I used information we had from our previous labs to create the background scene, the original aeroscale, the plot, as well as the size and shape of our ball trail and origin. I then programmed my initial conditions of the ball's mass, the ball's initial position, the ball's initial velocity, and then our gravitational constant and j hat vector, as well as our b coefficient. And I started the time and delta time. For the calculation loop, I used a while loop while t was less than 1.5 seconds. And then I first calculated the force of drag, the force of weight, and then F net was combining the two. So for the drag force, I did negative b times ball dot velocity, and for the weight, I did negative ball dot m, which is the mass, times g times j hat. I then used Newton's second law and the momentum principle to update the ball's velocity and ball's position, and then I incremented the time. Lastly, I finished by finishing the aeroscale to also help with the visuals for our code. And this is one of the final graphics, and this is the second graph that describes my ball's motion. So in order to calculate the energy exerted by our object, I use the energy principle in these equations. And then we know that the total active calories one should burn in a day is 750. And so by multiplying that by our conversion factor and dividing this energy by the energy we need to burn those calories, we now know that one needs to throw this object 378 times to burn a total active calories of 750. So when we compare the predicted model on our computer with our experimental and observed model, we realize that the computer predicted model that includes both the force of gravity and the drag force is a much better model. Some errors that could have caused the difference between our two models is just the fact that the first model is all human error probable. One thing that could have happened was the time interval that we chose. If we didn't take into account if we did the original force from our initial throw, that could make our models differ. Also, I may have messed up or been inaccurate in estimating the center of mass of my object at each frame while using Tracker. And lastly, the perspective of my video was shot in a different view than my other labs, so there could have been error from that.